Greetings. I'm Narayanan Komarath. My co-authors are Satyajit Meti, Rohan Ramachandran, Nandish Hiramat, and Ravi Deepak. Any approach to counter climate change must have assurance from climate predictions to avoid adverse effects. We may be sure, but that's not going to be enough. The scientific opinion has to agree. Such predictions need worldwide continuous detailed data. Meanwhile, wildfires are causing increasing damage and undoing many of our carbon reduction efforts. We synergize these two problems or these two needs into a solution using HALE or high altitude long endurance reflective UAVs. They're reflective meaning they reflect sunlight, otherwise they would burn up. Reflective UAVs that do routine meteorology and detect wildfires while those fires are still very small and one can act swiftly. I have a 1-minute movie. Wildfires are often started by lightning, then grow rapidly. Today's space-based sensors are 400 kilometers above the ground, too sparse and too infrequent to provide definite wildfire info in time. False positives are also a major concern. The images are just so small while the fires are small. Our approach is to float high and medium altitude solar powered UAVs that can operate from small unprepared ground, do meteorology, loiter over high risk areas, detect fire definitely, and convey warnings to space and ground assets. Our 8-meter flying leaflets are used to form 72-meter ultralight perpetual flying leaves. They can do meteorology along with remote sensing and fire detection. We are now preparing for coastal weather mapping, expanding to the entire Indian Ocean area. In brief, combating climate change depends on computational predictions, and that depends on continuous weather mapping to develop and validate. Early detection of wildfire is also a pressing priority. Our medium high altitude vehicles enable all of the above. Weather mapping over ocean areas will use our summer follower swarms of flying leaves that can then use the fast polar winds, south polar winds, to circle Antarctica as well during summer. So our solution architecture that you briefly glimpsed before uses just two types of UAVs, 8-meter span flying leaflets and 72-meter span flying leaves formed from 9 of these with much of the weight removed and brought down. These flying leaves are then perpetual. They are not just long endurance. They are mid-stratosphere reflective platforms. So we plan to have these swarms of flying leaflets and flying leaves used individually and as elements of virtual aperture multispectral antennae. Synthetic aperture radar can be done from them as well, measuring weather doing remote sensing of surface phenomena and detecting incipient wildfires day and night. The virtual aperture antenna concept is well known for swarms of microsatellites in low Earth orbit. Here we use mid-stratosphere platforms between 18 kilometers and 32 kilometers altitude. We get an order of magnitude better magnification, as you can see from the graph there showing distance, height in kilometers and the magnification. And you can see the difference between being up way above 90 kilometers at 400 kilometers and being between 18 and 32 kilometers. These also have very long persistence over high-risk fire areas, unlike very fast-moving satellites that move at least 7,500 meters per second. Ours move at maybe 50 meters a second or slower. And we can have constant real-time communication to satellites and to ground. A summary of applications is shown here. You need these to see into deep valleys and steep hillsides where fires might start, and to see around and through cloud cover. We can do tropopause vertical daytime wind profiles, for example over the Lakshadweep Islands and other island chains. We can do ocean surface monitoring. The FLT refers to flying leaflet and the FL refers to flying leaf. We can map stratospheric winds. We can do remote ocean weather monitoring, climate prediction data continuously. Fire detection, island chain microclimates, for example over Mauritius. Confirmation of fires very swiftly, 10 to 20 times better image resolution than from space. Also, we can monitor the fire risk by looking at vegetation and weather, and the virtual distributed antenna multispectral imaging and synthetic aperture radar to see through clouds and smoke. The next slides compare parameters. The flying leaf is formed in flight from 9 flying leaflets, with 6 of the 9 heavier parts returned. So the flying leaf achieves unprecedented low wing loading. People keep asking me, why are you able to do this when other Solar Pathfinder, Solar Impulse, etc., high altitude, long endurance vehicles are not able to stay there more than about 3 months. We can stay as long as something doesn't break, and that could be 30 years. So it achieves unprecedented low wing loading as well as a high aspect ratio, the long span, smaller chord. And this enables it to achieve perpetual endurance above 18 kilometers or 60,000 feet. By perpetual endurance, I mean if it doesn't have to glide for more than 12 hours, if the night is not longer than 12 hours, that it won't come down below 18 kilometers. It will never come down to where there are disturbances in the atmosphere. It will be smooth air. So there are various advantages to doing this. The glide profile is shown here. Nothing very exciting about it. It starts at dusk at about 30 to 32,000 meters and glides for 12 hours, and it's above 18,300 meters at that point when dawn arrives, and from dawn it starts climbing, and then back up to dusk maximum altitude of 31,500 or 32,000 meters. The chart on the right shows the wing loading, weight divided by surface top surface area, and you see that you reach the target of 1.25 newtons per square meter, which is extremely low, and that can be done if you have 9 of these flying leaflets joined together with 6 of the heavy parts brought down. So the flying leaf never has to enter controlled airspace except for end of life touchdown on water. Compared to CubeSat arrays, which is the other idea that people are pursuing for things like fire detection, the flying leaf arrays achieve far better magnification and persistence over interesting areas, because the flying leaf moves very slowly, extremely slowly compared to any satellites, along with very low launch costs. CubeSats, even though you can launch many, still require a rocket launch, an enormous amount of energy expended. We don't. Any energy that we spend is coming from the sun. Compared to other UAVs, such as the military Predators, MQ-9 Reapers, etc., those have very long endurance, 36 hours or more at this same kinds of height that we can achieve. But they use expendable fuel, and typically those need 2 operators per vehicle. The cost, as I have seen from some places, is far higher, and the numbers of these things that you can afford is far lower. So the flying leaf is far cheaper and can be mass deployed. So in conclusion, these high and medium altitude solar powered ultralights provide an integrated solution for weather data collection, remote sensing and emergency response, including wildfire detection. Large virtual aperture antenna and detection through clouds are possible. Thank you.